Welcome back, dear friends of the Sparkr podcast, to this new addition to the series of conversations with outstanding changemakers and innovators. This episode will be an insightful deep dive into the fascinating world of quantum computing, a technology platform with the potential to revolutionize how we tackle climate change, the discovery of new medicine or materials, and many more applications throughout the business world and society. Today, I'm in conversation with Damir Bogdan, the CEO of QuantumBasel. QuantumBasel's mission is collaboration and seamless access to the world's best quantum computers, and thus enabling breakthroughs across industries. QuantumBasel offers companies, startups, and leading research institutes access to quantum computing and high-performance computing, and with that, laying the foundation for tackling future challenges in the life sciences, industrial manufacturing, logistics, and more. In addition to his role at QuantumBasel, Damir is also CEO of Actvide, a consulting company specialized on transformation within the digital age, active in Switzerland and Silicon Valley. In this conversation, we will touch on several topics, ranging from a glimpse into the basics of quantum mechanics all the way to the concrete examples of how quantum computing can lead to game-changing efficiency gains in logistics and many other areas. So please enjoy this sometimes a bit mind-bending episode of the Sparkr podcast with Damir, which was recorded in the inspiring surroundings of QuantumBasel. Hi Damir, it's a great pleasure to have you on the Sparkr podcast to talk about quantum computers.
I'm very glad to be here.
So I'm sure that many people have already heard of the vast potential and the implications of quantum computing and quantum technology on many critical elements in our lives, like breakthroughs maybe in health and medicine, developing new materials, or encryption, of course, also a very big topic. So before we dive into all of these big implications of quantum computers, let's set the foundation and give, so to speak, an executive summary on quantum mechanics. So the building blocks or the basic principles of how quantum computers work. That's, of course, amazingly complicated and mind-boggling, but still maybe we can radically simplify it so that we get a better understanding why quantum computers are so different from normal computers. So that said, could we talk about the concepts of superposition and entanglement as two examples? Of course, you have to simplify a lot, but I know that you are great at it, at translating the quantum world into the language that normal people can understand. So can you please give us a summary or a simplified answer of what something like superposition means and why it matters for quantum computing?
So the task is rather impossible because explaining some things in a simplified way that everybody understands makes it not being correct. And explaining something in a way that it is correct, nobody would understand. And there's a saying in the world of quantum physics that the one who says he understands quantum physics is a showcase that he does not. So let me try to find this balance. And you've asked about superposition and entanglement. Now, first of all, perhaps we shouldn't use the notion of a normal computer versus a quantum computer, because what's today normal, tomorrow's a new normal. So I rather talk about classical computer and quantum computers. So a classical computer, how does a classical computer works? The classical computer has these transistors, which are on the chip, and the transistors have the so-called bits that represent states of 0 and 1. And the bits are the smallest unit of data. And they're always strictly representing either 0 and 1. And over the last 5 decades, with Moore's law, we had the fact that every 18 months, the number of transistors on a classical chip doubled. And that means a classical computers with zeros and ones, when you've got the double amount of chips, of transistors, you've got a double performance. And so this binary system, as we know it, while powerful and sufficient for a vast array of computing tasks, is fundamentally limited given by the inability to process information beyond these two states of any given moment. And this starts now, this is where quantum computing comes into the game. And as you said, I had to explain it in a way that it's understandable. I want to make one statement up front. The question never will be either or. The future is hybrid. So whatever the future will bring, it will be a hybrid between a quantum computer and a classical computer. So superposition, coming back to these bits, which are binary. In quantum computing, we also talk about bits, but they are so-called qubits. And they exist not just in this exact state of 0 and 1, but also they represent both states simultaneously, unlike the classical bits. And this is not just, how shall we call it, the theoretical curiosity. This is something that allows quantum computers to perform a million calculations at once. For example, if a classical computer with 3 bits can do 8 operations in parallel, this with a quantum computer can be done the same. However, when you want to double the performance of a quantum computer, you just need one single bit in addition to the existing ones. And this makes it exponentially more performant in many ways, which I can explain later, than a classical computer. Because with 10 qubits, you already can have more than 1,000 states in parallel. And with 20 qubits, we've got already more than 1 million states that can be calculated in parallel. And with 166 qubits, even more states than there are atoms on this planet. So this is a massive parallel processing capability. And this is pivotal to certain things which I will talk about later, like simulation, optimization, machine learning, or important for cryptography. So superposition, to make a summary, is based on the physical of quantum physics, based on these principles, allows all the states between the 0 and 1. Like if you flip a coin and you see at the same time the back side and the front side. On the other hand, there is another physical phenomena, which is called entanglement. And 100 years ago, nearly 100 years ago, Albert Einstein already recognized this entanglement. Entanglement is a phenomenon where qubits become so interlinked that the state of 1, no matter how far apart, instantly influences the state of another. So that they are somehow entangled. They interact. And this is crucial for quantum computing because it introduces a new level of complexity in the way information is correlated and processed. So back to Einstein, he called it a spooky action in a so-called far distance. He couldn't explain it. He couldn't prove it. He just saw that some atoms must be correlated to each other. And so this was entanglement. And it is not more than 1.5 years ago that the Nobel Prize in Physics of the year 2022 was awarded to Alan Aspect, John Clauser, and Anton Zeilinger from Austria. And one thing they did is that they proved that superposition is here. They did not explain it. They could not prove why it is here, but they had the ability to prove it. And so this led already to a Nobel Prize. So to summarize, a classical computer calculates in bits. He performs all his algorithms in sequence, one after the other. And if you want to double the performance of a classical computer, you need the double amount of bits. A quantum computer has got qubits. If you want to double the performance, you need 1 qubit more. And it calculates the algorithms in parallel, which makes it much more faster and more accurate in some calculations. However, a quantum computer has also some limitations we will talk about later.
Excellent. Thank you so much for this compelling introduction to these critical concepts of quantum mechanics and their influence on quantum computing. So you already indicated that these are not just faster classical computers. They are fundamentally different in the way they operate. It's much more an exponential system and less a linear system. So many differences. And now if we look at the different areas where they can be applied. So I would assume that there are certain areas where a classical computer is perfectly fine and other areas where a quantum computer can really shine because of their properties. So could you explain to us why quantum computers are superior in areas like simulating complex systems, finding patterns in huge amounts of data, and all the areas where they are superior? Why are they so more potent than the classical computers that we know at the moment?
If I look at quantum computing, then there are 3 fields which are of particular interest. One is optimization, simulation, and machine learning. So these 3 problem types tend to use a lot of data, and they need a lot of computing power. And if you look at the computing power generated by classical computers today, then it's a given fact that due to the Moore's law, which is flattening out, I was talking before of transistors. So 2017-18, there were the 7 nanometer transistors. Then the 5 and the 4 nanometers have been introduced. Some say even that the 2 nanometers transistor will probably be used by companies like Apple. However, there was a kind of a physical barrier between the cost efficiency and the cost and the efficiency of those classical chips. And so we think that, coming back to the question, these calculations like optimization, machine learning, simulation, they consume a lot of data. They need a lot of data. They need also a lot of data to be trained. They consume a lot of performance, and these high computational resources are on the long end limited with classical systems, because training and running complex AI models alone often requires high computational power and storage, and this makes it costly. And they often struggle to generalize from their training environment to new unseen situations. So they have to be trained. It makes it necessary that they have to be trained on with huge data volumes. So to cover all these possibilities, and learning on the fly is difficult. And now some statistics say that since the invention of ChatGPT in December 1.5 years ago, before that, the worldwide energy consumption of data centers was at about 8%. We now already are at about 13%, with some countries like Ireland already being up to 17% due to the huge data centers they've got there. So if you combine these things, you know that optimization, simulation, and machine learning consume a lot of performance of the classical computers. The more performance is consumed, the more energy is needed. So, and the classical computers, Moore's law is flattening out, won't be more powerful over time. That makes it quite understandable why, since a decade, scientists are looking for new kind of computational power. Now, quantum mechanics is an old principle, as I told you before. Even Einstein knew about that. But the first commercial usable quantum computer has been introduced in 2016 by IBM. Now we are in 2024. So within 8 years already, a lot of companies started to talk about quantum computing, because the ability of a quantum system is to calculate in probabilities in parallel. It does not calculate all the solutions in parallel, but with a high probability, it calculates a lot of solution in parallel, which then leads to a good enough result. And this makes it extremely speedy and accurate towards a classical system.
Very interesting. Is it possible to give like an educated guess? You mentioned ChatGPT, large language models, machine learning. As we all know from reading the news, training such a large language model needs a huge amount of data, energy, time. Is it possible to make an educated guess what the factor of, let's say, improvement is if you would use a quantum system in the future for such a large language model training? Is it possible to make an educated guess just to get a sense of, to make it a bit more tangible, of what kind of magnitudes of improvement we are talking about here?
You know, the question is, what is the measurement? So if you take one axis, which is the energy consumption, then sources say that Googling, let's say, with ChatGPT or searching something with ChatGPT consumes up to 30 times more energy than a traditional Google search. Alain Aspect, the Nobel Prize winner I've mentioned before, said that perhaps the real advantage of quantum computing might lay in 100, perhaps even 1,000 times less energy consumption. So if you look at today's system of a quantum system, a physical quantum system consumes within the megawatts. So no matter if it's 100 or if it's 10, 20 or 100, it's in the kilowatt region. If you look at supercomputers today, they consume energy in the megawatts. So this is a factor 1,000. And so this brings me to the next measurement which you can take. And this would be speed. In some arithmetic or mathematical calculations, not in all, but in some. Quantum computer can bring results within minutes, whereas the largest supercomputers worldwide needs thousands, if not 10,000s of years. So it does not matter if it's 10,000, 100,000, or even if you take 1,000 years. The comparison here is years versus minutes. Yet, this does not mean that a quantum computer is always speedier, because in some basic function, a quantum computer is not good enough. So, in theory, quantum computer can process complex problems much faster than classical computer. However, in some points, a classical computer is better. And our quantum physicists, which are writing the algorithms together with the industry partners, they, at the beginning of a project, they formulate the problem, meaning they slice it into very thin slices, and then they say this part of the algorithm is better calculated on a classical computer, and this is better on a quantum computer.
It's the hybrid system.
That's the hybrid system I'm talking about. And the fourth axis where you could say comparison between classical and quantum computer, and this is the last one, is its accuracy. So you can calculate, let's say, an easy example. You've got the central warehouse. You've got 5 trucks, 4 goods to deliver, and to 70 different spots. So you give a classical computer a half a second computing time to calculate this, a hyperscaler, whatever it is. It will come to a result. You send the trucks out. All the goods are delivered. By the end of the day, you check how many kilometers they did. And in those examples we saw, let's say, this was 28.5 kilometers. So you do the same calculation within the same computing time with a quantum computer. And the trucks come back with 22 kilometers. So they've spent less fuel. They were faster. So the result was more accurate.
Thanks for making that example, because that's the place that I want to go with my next question, which is kind of zooming in a bit more on the strength of the quantum computers and their huge potentials. If you read about quantum computing, you could think that they will solve every problem on Earth. They will solve climate change, heal cancer. But also, on the other hand, they will be very dangerous because they can destroy our current encryption models and so forth. Maybe let's start with the more doomy scenario of the encryption problematic, and then go to the positive scenarios like the one you mentioned from logistics. Let's try to end on a positive note. So let's scare some people first with the encryption topic. But spoiler alert, there's also some good news when it comes to encryption, because not every encryption model is prone to being cracked by quantum computers. There are also solutions out there in the market. But let's dive in. That's something that I'm quite sure many people have heard about quantum computing or associating with quantum computing, that once they will reach a certain maturity, they will be able to crack our current encryption system, which has, of course, huge implications on all the financial systems with payments, savings, all the health data, national secrets, nuclear facilities. The list goes on and on. So encryption is really, really key in our digital world. Could you explain to us what is going on here in this doomy scenario? And is it adequate to be so apocalyptic about it?
You know, there are always these doomsday prophets who tell us the new technology which will lead to whatever is happening. And I will want to quote, there was the Guild of the Writers in Hollywood. And they start to say the introduction of this new technology will destroy the jobs, and they have to now come together to fight against this. It will destroy the creativity. It will destroy everything what they stand for. And so they tried to revolutionize, tried to start a revolution against the introduction of this new technology. So the scenario I'm describing right now was the scenario the Writers Guild in US, in Hollywood, described back in 1970 when the first copy machine has been introduced. And so I know you first thought I'm talking about ChatGPT now, and I'm not. So profiting in doomsday is always simple. However, there is a reality behind that. And it's not that quantum computers will destroy cryptography. Cryptography is based on some mathematical principles. And those mathematical principles, like the RSA encryption, which is the mostly used encryption, is based on the so-called private key and public key. And this works in a way that you multiply two huge primes, so two huge numbers, with one with the other, and then you get a bigger number, an even bigger prime. Now, calculating a multiplication between two large numbers can easily be done by every single computer, classical or not. Now, if you only have the result to factorize, this means to find out which two numbers multiplied led to this result. This is something which classical computers could not do and can't do. However, there was a mathematician called Peter Shor who introduced in 1994 an algorithm which is able to factorize these numbers. However, in 1994, there was no computational power, not even on the horizon, who would ever be able to do that. Quantum computing will have this computational power. And the moment this will happen, then with the help of a quantum computer, today's RSA encryption can be made transparent, can be read. Now one could argue we do not know when this is, and this is correct. So, and also, is it the Chinese that will be there first, or is it the US or Western countries? One do not know. But we do know that there are about 75 billion devices connected to the internet. We do know that 95% of the encryption of the web traffic is encrypted. And with Shor's algorithm, with quantum computing, the so-called Y2Q, we all remember Y2K, which was the year 2000. So in difference to the Y2Q, we knew the exact date of Y2K. But Y2Q might come in 3 years, in 5 years, in 10 years. However, we have to start think about now, because there are, let's call them organizations, who are harvesting, they are trying to copy all the data which is encrypted over the net and put it in a safe. And once a quantum computing is here, their idea to take it out of the safe and then to decrypt it with the help of a quantum computing. So all the RSA. And this is the so-called doomsday, that all the today's encrypted communication will be once decrypted. So is it in 3 years, in 5 years, in 7 or in 10 years? We do not know. But when this happens, then you can go back and say, these have been your health data 7 years ago. These have been your tax data. These have been your transaction. You know what? Even the blockchain based on RSA can then be calculated. So this is the doomsday. However, scientists thought about that. And so the National Institute for Standardization and Technology, NIST, started to think about quantum safe encryptions. And last year in 23, they came out with a set of 4 different encryption patterns, of which 3 are so-called lattice-based and 1 is hash function-based, which means these are different kind of mathematical equations, which even with a quantum computing won't be tackled that fast. And we are particularly proud that 3 of those standards have been developed in the IBM Research Lab, also in Rüschlikon. So with 3, with Crystal Kyber, the Lithium, Falcon, there IBM has been involved, and there's a 4th one, Sphinx Plus, and 3 are for digital signatures and 1 is for encryption. And so the standards will now be declared as de facto standards by NIST, and the final standards then have to be adapted by ISO, ANSI, ETSI, all these standardization institutions worldwide for telecommunication, for computing and everything. And then one can say, we are safe. And in US, all the agencies already have been asked to implement or to make a plan how they try to implement those standards so that the data, even today's data, which is not encrypted with these standards yet, will not be readable afterwards. However, one can say, okay, we wait these 3, 5, 10 years because it's not possible now. But coming back to this harvest now and decrypt later, this is the reason one has to start to adapt now. And this is what we start to conduct, those kind of projects together with our technology partners. How can one make sure that today's encryption won't be hacked by a quantum computer?
That's very fascinating. Thanks for also pointing out the harvest now and encrypt later method. That's, I think, a very important concept to understand that this is possible. And what I always like doing in these podcast conversations is, first of all, sharing the deep expertise, the knowledge, as you are doing now, but then also giving like first steps or some insights on how can now, let's say, a CEO or a member of a board of directors or a strategist in general, how can they now take maybe a first step? Who should they talk to? What should they have on their radar? What should they read? So I will ask this question a couple of times, but now focused on the encryption topic. What would you recommend to people in positions of power, responsibility? Where should they look? How should they act to get started right away?
Well, first of all, perhaps the question is who is concerned or who should be concerned? Everybody using the internet, digital signatures, critical infrastructures, financial services, systems, blockchain, enterprises as such, like email. So at the end, it's industry agnostic. So what one should do is to make an overview, a strategy. Where are your crown jewels? Where is the data nobody should know? Not today and not tomorrow. And so what kind of software, firmware are you signing with? What kind of web browsers are you using? What is your network equipment you've got? What is the operating system? What is the niche equipment? What are the custom applications and legacy systems you are using? And then with this inventory, you have to start which are the standards used today and where do I have to adapt? And you don't have to adapt everything with the highest standards, but you have to be aware of that. And so you also do not need, when you once introduced quantum safe encryption, this is important to understand, you not necessarily need a quantum computer to decrypt and encrypt and decrypt again. There are standards there are quantum key distribution standards, there are quantum random numbers generation standards. This is the post-quantum cryptography. Everything has more or higher level of security or less, but it wouldn't make sense if we now start to decrypt a mail with perhaps it's a very important mail with a quantum system as such. So you do not need a quantum computer in every sense. There are also some hardware providers which say that they are secured with quantum safe algorithms and things like that. So coming back to our question, one has to do a portfolio and has to think about how is this endangered, and then those new standards have to be implemented, and therefore we help industry partners to develop a strategy, and this is the beauty of a neutral hub like QuantumBasel. We've got different kind of technology providers. Now, I already named who is predominant in the phase of these new standards. So then, together with our partners, we then can help to secure the future crown jewels. And as I said, the best moment to start with this project is not tomorrow, is not today, but was perhaps yesterday. The second best moment is to start now.
Hi, this is your host Christian speaking. I hope you enjoy listening to this conversation as much as I did preparing and moderating it. It's one of my specialities and passions to unlock the wisdom and insights of exceptional people as a moderator and facilitator. So if you want your next strategy workshop to be a success or want to engage in productive individual sparring sessions as a leader, let's get in touch. Check out my agency, Sparkr, which serves changemakers and innovators. Learn more on the website www.sparkr.ch. That's SPARKR.ch. You find the link in the show notes. And now, let's spark you up and get back to this inspiring episode of the Sparkr podcast. Thanks for the wake-up call. Very clear and urgent, I would say. From this rather doomy scenario, let's move on the bright side, because as we all know, quantum computing has also a lot of potential. So there has been, for example, McKinsey writing about or releasing a report called, I think something like, "Can Quantum Save Our Planet?" Yeah, so big questions, big promises. You already mentioned hinted at an example of a logistics use case with optimizing the route or the distance that is required by trucks to deliver certain goods. Could you please give us some examples on this, let's call it bright side of quantum computing, how it can have a positive impact, be it in the climate sector with, let's say, optimizing or reducing energy consumption, or in life science with drug discovery or logistics. I know that there's also a quite remarkable example with the optimization of the logistics at the harbor of Los Angeles. So could you give us some concrete examples to also get a glimpse at the positive implications?
Okay, so if you go back and say what I've explained before, quantum computing can be used within, first of all, optimization, simulation, and machine learning. So given this fact, one has to think, so what are now the applications which need either optimization, simulation, or machine learning? And applications can be within logistic, marketing. We've got use case in marketing. They can be in everywhere where it's manufacturing, big data, chemistry, cryptography already talked about, materials. And if you have this application, you can then map it to different industries. So at QuantumBasel, we are focusing on 4 industries. And this is in the order of adaptability. The one is industrial manufacturing, simulation, optimization, plus logistics, optimization. The third one is financial services. There, many things can be done in the field of risk calculation and so on. And the fourth one is in life science. And what we did, we've broken down every single part of, let's say, one industry. If you go to industrial production, so what are use cases? Use cases can be routing and optimization. Use cases can be improving of materials, supply chain optimization, workforce scheduling, quality control, autonomous vehicles, smart maintenance. And everywhere within that, we've got different kind of use cases. Let's say one was improve the design and the reduce the cost of HVAC optimization. So one customer of ours, HVAC, so air conditioning, everything you see on the ceiling of a complex industry environment. So you've got this different HVAC systems going through and so on. So if you build a single house for your own, there is no big complexity. But building a complex industrial manufacturing building requires a lot of planning where to route those HVAC systems through. And we've conducted this complex simulation with a quantum computer. We therefore used an annealer from D-Wave System, one of our quantum partners. And having that said, the goal was to maximize the comfort and the efficiency and to minimize the environmental burden, like fuel consumption, emissions, delivery time, and cost. And the result was tremendous efficiency gains in reduction the length of the whole HVAC design, so less material. There were less crossings, and this means that there is less energy needed to blow the airflow. And the third one was a dramatically improvement in the time to calculate the simulation. And this is a use case which we have conducted together with our partner. And this hopefully will soon go into production. So there will already be production use cases. So this is industrial production. If you go to logistics, another partner of ours, also an example with perhaps Airbus. The Airbus is working on quantum aircraft loading and optimization with IonQ. And quantum machine learning is the basis. And as I said, that machine learning, which comes perhaps to a limit using classical computers, because of the more diverse the data, the more computational power you need. And so with Airbus, the cargo plane loading tried to be optimized in terms of balancing out the whole airplane and to fill it as good as possible. So this is one there. And another one you mentioned was the Port of LA, which hopefully will be expanded to European ports this year, 24 as well. We are working on that right now at the moment. So the Port of LA example was, this is a huge container port, and this has been, a pier has been optimized with the help of quantum computer. There were digital twins involved. So you first had to build up a digital twin and to test the various optimization options. And at the end of the project, there was a 60% increase in delivery by crane per day. So every single crane, instead of 60 containers, shipped nearly 100. The truck turn time, where trucks had to wait for its load, came down from 66 to less than 58 minutes. And the crane utilization went up from 45 up to 72%. These are clear results by an optimization. So I can continue with that. Perhaps one example of the financial services industry, there the near-term use cases are pricing and risk calculations, portfolio optimizations, the creating of hedging agents with synthetic data. This is something important as well, because when you run a Monte Carlo simulation, you need this kind of data. And this isn't that easy to do with classical computers. And let's say a quantum computer outperformed the classical AI with 20 up to 1,000 times fewer iterations, and up to 4 times less data needed to train the AI. So if you have less iterations, if you have less data to train, that means scalable models and less energy consumptions. So you see, I already now conducted from the different use cases. And let me, before we can still talk about chemistry and life science afterwards and protein folding and all that. This is perhaps more on a long shot, but because there are the calculations there are that complex that even a quantum computer, how we can imagine today, can't solve those problems yet. There are other things you can always start with, and it's never too late to start with those kind of things. But let me finish, perhaps conclude with AI overall. If you look at what can be done with quantum computing, and coming back to this McKinsey report you mentioned before, in climate science, quantum computing could model complex environmental systems with accuracy which hasn't been here yet. It offers insights into climate change mitigation strategy. It can promise that they go into near real time simulations instead of to simulate what could happen based on historical data. And I'm not yet talking about the energy consumption of a quantum computer. I already told that. I'm also not talking about the energy consumption of AI models, which is rising and rising. I'm now talking about to predict and simulate climate changes on site in perhaps real time, which makes it easier to act and to react on incidents. And only this part of it is perhaps something which McKinsey is referring to as well.
So what I'm hearing in all of these fascinating examples is, or oftentimes the examples were about remarkable efficiency gains. So that's, of course, when you optimize things that quantum computers are good at, you are making efficiency gains. But what I'm also wondering is, in the wide array of use cases, would you say they are mostly about efficiency gains, or are they also sometimes or most of the time about, maybe let's call it disruptive breakthroughs? Or maybe in other words, are we, when using quantum computing, are we more talking about increasing efficiency in existing business models, or in a existing business mindset? Or is it that quantum computing kind of unlocks or breaks completely new ground with new business models, with a new business mindset, and so on? How do you assess like the potential in that regard?
At the beginning of the podcast, I have been talking about exponentiality. Now, if you look back in the 90s, when the internet has been first introduced, who ever could have predicted what once will be possible with the internet? And the same when iPhone has been introduced in 2007. And whoever could have predicted that business model will change that fast? And I think that the combination of two technologies always led to something which can't be predicted. Let's say when Henry Ford introduced the Model T, he did not neither invent the car nor the construction belt. The construction belt was there in agriculture. The car was there since 50 years. But the combination of these technology led to the fact that within less than 10 years, all the roads within New York changed from coaches to cars, with all the professions behind, with everything. All the business model changed. So is it possible to predict with the combination of AI and quantum computing, where I say AI is, with quantum computing, it's like AI on steroids. You can't predict what will be possible. So it's hard to answer. However, I think that it's not just optimization. As I say, machine learning can be enhanced and most probably also speeded up. So it can be trained with less data. The second point is simulation, wherever this is possible. Optimization, these are one thing. So what will be possible within a decade? I do not know. One also has to say quantum computers have also to improve. New materials are needed. The phenomenon of entanglement is still here. The coherence time, which we haven't talked about. Coherence time means how long can you calculate on the grid with qubits, because they tend, as soon as you start to measure them, they bring on wrong results. So they have to be stabilized for a long time. To stabilize it, today's quantum computer have to be cooled down to 5 nanokelvin perhaps. So there are a lot, and so the companies are now trying, there is a race of more and more qubits going on. However, they also found out that perhaps not more qubits are important, but better qubits. So what is the aim of a supercar if it's always in the service, in the garage? So perhaps less qubits, but then more quantum computers serialized. So perhaps the future is that you've got 1,000 quantum computers, but everybody with only 20 qubits each, but then they are stable. So we do not know what they bring. But when you look at all the figures, at the amount of money flowing into quantum computing from governmental side, startups, and so on, when you look at the technology proceedings, one can say quantum computing will turn many industry. And all the industry with machine learning, I do not know one which is not involved there. With optimization or simulation, those are the use cases.
I think it's funny that you mentioned the automobile as an example of how you can never really predict what this introduction of a completely new technology or platform has implications down the road. Could you maybe give us a comparison, maybe not with the automobile that you mentioned already, but with transistors? Let's make the comparison to the classical computers where, let's say, in the 1940s, 50s, 60s, transistors were invented, mainframe computers by IBM and so on came on the market. Is quantum computing in this stage, roughly speaking, of transistors being invented, mainframe computers, or is there maybe already a kind of a Macintosh moment around the corner? How would you make the comparison to this timeline of classical computers that we all know?
Well, it took in the old days decades until a new technology came through. And I mean, as you mentioned before, transistors were there around long time, and then the 50s, 60s. I mean, it was the former director of IBM, Watson, who once predicted, I think this was early 50s, when asked how many personal computers do you think there will ever be needed worldwide, he came up with the prediction of, well, I'm sure there will be about a potential of 10. So here we are. And I mean, the personal computer was possible with Bill Gates, DOS, when he bought DOS from IBM and he created the Windows. And so the first personal computer really established in the 80s. Internet came in the 90s. Combined with that, then we started to have mobile phones, and then we had smartphones. And none of the competitors of smartphones survived none of the competitors from one wave to the other survived. So the smartphones like BlackBerry and I knew, but when between the mobile zone and the step to the smartphone, there was new people, like new companies like HPC, iPhone, Apple, and so on. So coming back to your question, no, quantum computing hasn't had its iPhone moment or its ChatGPT moment yet. When will it be? I do not know, because this is exponentiality. It will come faster as we think, I guess. The speed of change never has been that fast as it is today. At the same time, it will never be as slow as it is today. It's one say that quantum computers are in its infancy, but I can give you one prediction. Based on all the aspects we see, we think that the so-called quantum advantage moment will be possible in this decade. And we will talk about that on our quantum symposium, on the Global Quantum Symposium, in March, mid-March here, with all the professors from many universities, industry speakers, and there will be also some announcement be made. But we expect, based on all this, that quantum computer will have its advantage, quantum advantage within this decade.
I think that's a beautiful place to end this conversation, even though we could go on for hours and hours. But maybe there will be a part 2 in 1 or 2 years when quantum computing has yet reached another stage completely. I think you masterfully showed the potential, the urgency to commit or to engage with quantum computing, no matter the industry you are in. So as a closing remark, I would like to give you the opportunity to tell the audience, where should people look to find you and look to find QuantumBasel, or what other resources would you recommend to CEOs, strategists, to get engaged with you at QuantumBasel or other important players in the field? What should they do once they have finished listening to this episode?
Well, first of all, for everybody who's still listening, because usually when I start to talk about quantum computers, perhaps I'm not that interested. So thank you for all that stick until the end. It's a very good question. I want to answer this way. Well, you can find us over the internet, quantumbasel.com, this is for sure. You can always ping me over LinkedIn. What we do, we try to understand the company's problems. So we explore. In the explore phase at QuantumBasel, we foster a comprehensive understanding of quantum computing to the managers, to the technical staff, but we also tried to understand what are the problems. In the second phase, we try to enable. So in the enabling phase, we train managers or also technical people how to use quantum computing, because we don't want to do this all on our own. We want the people be trained. We want to have champions, future champions. And then in the third phase, there it's about engagement. And engagement is, let's try out, demonstrate. Let's try out the proof of concept. Like this HVAC example. This was a proof of concept conducted over a period between 7 months it was about. And so at the end of this third phase, one has a process which is optimized, whatever. So I think it is important now for industries to start to conduct this project, to understand, to use a neutral, and this is our USP. We are a neutral hub. So we do not have one technology. A company comes to ours with a problem, and then it can choose between, we will try to make them understandable which technology is the best to use for this very problem. And then we help them, we train their people, and then we conclude first projects. And last sentence, training people. It's also important to do a lot with students. And this is why we are collaborating with many universities. We are allowing them to access our systems so that the workforce of the future, the students, can be empowered as well, because this is the most important fact.
Thank you very much, Damir, for these very inspiring or interesting insights, and also for all the work of you and your team and what you are building at QuantumBasel in Switzerland. It's fantastic.
Thank you, Christian. We are proud as well. Thank you.
Thanks again to Damir Bogdan, CEO of QuantumBasel, for this insightful conversation. If you like this show, please leave a positive rating and share it with a friend. For more exciting conversations with leaders and changemakers in technology, innovation and entrepreneurship, please consider subscribing to the Sparkr podcast wherever you listen to your favorite shows. In the Sparkr podcast catalog, you find, for example, a deep dive about battery technology and its role for a greener future, an introduction to blockchain technology and Bitcoin, or a conversation about the societal impact of AI. Also, you can find inspiring episodes with leaders such as Thomas Zurbuchen, former chief scientist at NASA, or Urs Hölzle, employee number 8 of Google. I'm looking forward to welcoming you back to another episode of the Sparkr podcast, where I'll uncover the mindsets, tactics, and insights of exceptional people. And if you want to get in touch and work together on your next strategic initiative or innovation project, check out my agency, Sparkr, which offers leaders, changemakers, and innovators tailored services in strategy development and project management. Learn more on www.sparkr.ch. You'll find the link in the show notes. It was a great pleasure having you with me this episode. I wish you a great day and talk to you soon.